Most of you guys know me well by now, but for those of you that may not, I'm Ellie Peters. I'm the Dean of Girls at St. Augustine School and also teach. This evening, and the ones that will be a part of this conversation series, is actually the product of feedback that we heard from some of our core parents and members of our community. A couple months ago, we got a group together to just do some talking about what it would look like to take St. Augustine School and make our mission and our particular approach to education more known and more understood by people that are really at the core of our community. So obviously that's our current parents and our incoming parents, but also fellow educators, people that just quite simply care about education and would like to know what our approach is, and people that might be vaguely interested in the school in the future. So this is true of this event and other installments of the conversation series. Feel free to invite people. Anyone who wants to sit around and talk about what good education is like is definitely welcome. Our idea is that we're going to take different areas of our curriculum and have different members of our faculty say a few words on how we're taking our mission of Catholic classical education and then applying that in the classroom. And we'd love to bring that into dialogue with your observations and questions, and then of course, your students' experiences in the classroom day to day. So our topic tonight is math, and I'm going to welcome Steve Hendrickson, who is our Dean of Boys and also our math teacher.
Glad you got to make it tonight. So what is it that distinguishes St. Augustine's approach to mathematics from other schools similar to us, say classical education or other parochial schools or any other private school that is trying to do something with mathematics? And I've dug into this quite a bit over the last number of years. And what really I think distinguishes us from other institutions at this level is we take mathematics very seriously. If you look at classical education kind of across the nation right now, what they take very seriously is the humanities, the philosophy, the literature, the poetry, the Latin, and other languages, and maybe even the arts. And if you look at their mathematics curriculum, it's full of all sorts of options that you could take, full of things that you could go this way, you could go that way, and the level that you need to reach in order to graduate is very low. What we're thinking about is very different about mathematics. For us, mathematics is right up there with the philosophy. It's right up there with the poetry, in that it is one of the most significant human contributions that we've made to this world, is mathematics. And that makes it worth studying in and of itself. We don't really necessarily care if it's practical. We don't care if the sciences use it or not. Mathematics is a significant achievement, and we want to study that. So that's what makes us different, is that we're going to take it very seriously. We're not going to allow students to take a path of least resistance, for example. We want them to take very serious mathematical courses from the beginning through to the end. So how do we pull that off? Well, for the most part, if they come in the 6th grade and the 7th grade, those classes are designed to take students in from pretty much any other institution, anything that they've done, whether it's homeschooling or some other school, private, public, it doesn't matter. We just want to set a nice groundwork for them in order to take it, in order to build off of that into the other schools, or the other classes, sorry. Our most significant math class that we have here is our 8th grade algebra class. And the reason that's the case is because everything that we do in the high school really has an algebraic base. Okay? And so if they can get their algebra skills in a place that is really solid and they're able to see some things well, then all the other classes in the high school will actually be very successful. What we're looking for is to be able to see the patterns in the map. And then the symbols. In 8th grade algebra, we're doing what are called systems of linear equations, two equations of lines that somehow cross somewhere in the plane, and figuring out where it is that they cross symbolically as opposed to graphing them. And there was a point at which all 3 boys in the class I saw them, they had their pencils down, you could see their eyes looking and seeing. We're able to get to the result just by looking at it and seeing it and kind of doing the mathematics in their heads and kind of embracing this mathematics. One of the things that I try to instill in my students is that mathematics is not just this tool that we're trying to do. It's something that is beautiful, and if you understand it properly, you're understanding a piece of poetry, you're understanding a piece of literature, you're understanding something that is actually has this life to it. So I'm regularly giving them some historical data about this mathematician was the first to discover or develop this area, or where does pi come into all of this? Where does other constants like that come in? And I really want them to be able to appreciate the mathematics just for what it is. Most people that come in here that I've talked to as a lifelong math teacher they're math avoiders. They've had such terrible experiences with mathematics that the first thing they want to do is avoid it, take the least amount as necessary. But in my mind, those are the ones that have never really come into contact with authentic mathematics and been able to just simply have the joy of mathematics embed them and drive them into something. So, in order to really show you what this is like, I have a math problem for you to think about. Yeah, absolutely. So if you could take these and pass them around. Yeah, right. So what I have here is what's called the
Zeros and ones.
Oh.
This is what's called the ASCII code, which is the American Standard Code for Information Interchange. I'm sure I have you fully on board already. When you type things into a computer, excuse me, that looks really bothering me. When you type things into a computer, the computer remembers things based on numbers. It actually digitizes everything that happens. So it turns every keystroke into a number. So if I wanted to, for example, take the number or take the word book, if you can read what's going on here, there's 4 columns. You have the far left column, which is the decimal. You've got the binary, that's the ones and zeros, which is how the computers think. And then the actual coding is on the far right of each column. Now the first one on the left here, that doesn't really mean much to us, but the second column, you can see all the different symbols, numbers and whatnot, and then the letters start in the third and then the fourth column. So if you wanted to take the word book, you can find the lowercase b, and then go to the decimal, which is 98. Y'all see that? Okay. So, and then we've got 2 O's. So that's going to be 111, 111. And then finally the K, which is 107. And so this is a way of, so to speak, encrypting the word book into a number. When you think about a digital recording of something, this is what we're doing, is we've recorded the word book into a digit, into a number. Excuse me. Now to start out with, I want to talk about these things called the natural numbers. They're the things that are the kind of basic groundwork of mathematics. And it really is just the numbers and that's all I want to do. But it's all the positive integers, as we would say. So let's assume that I have no social life and I spend my time on Friday evenings or Thursday evenings talking about mathematics. And I wanted to write out the digits of the natural numbers, just write them out. Eventually, I would have to come to this number. And so eventually I would write the digit for book in my list of natural numbers, right?
Yeah.
Interesting. Well, if I did something like this, that's just multiplying the original number by 10, but it also is a different natural number that contains the word book, right? Book and something else, just gobbledygook. But eventually, in my writing out of the naturals, I would write the word book a second time. And if I did this, well, that's 100 times the original number, and it's a totally different number. And eventually, way down the line there, I would write the word book a third time. And then a fourth time. And then a fifth time, and maybe by now you can see what I'm getting at, is that the natural numbers don't ever end. They just keep on going. And in them, you can find the word book. How many times? Infinitely many, right? Okay. Well, this is the word book. If we wanted to, we could digitize the word sandwich. It'd be a bigger number than book because it's got more letters to it, but somewhere in my writing out of the natural numbers, you'd come across sandwich once, twice, 3 times. In fact, the natural numbers contain the word sandwich infinitely many times. I'm just going to pull a book here. We'll go with Dante's Paradise. Now, in our list there, we have all the punctuation, we have spaces, we have capitals and whatnot. And so we could even start here on the first page, a little biography of Dante. And we could actually make a digit of paradise, right? Even the contents, table of contents here, list of illustrations, and the introduction. All of these things we could actually make into one very large natural number. It would be very large. Like, I don't think this board could contain such a digit, but it would be a natural number. And I could put a 0 at the end of it. And we'd find Dante's Paradise a second time in this list of numbers, and then a third, and then a fourth, and so on. What else we got up here? A lot of Dante here. What is this? Looks like it's Dante again. How about we take Shakespeare? Hamlet. There you go, Hamlet. Hamlet you could turn into a digit just by simply going through every single keystroke that would be to type out Hamlet and converting it into the proper digits. The version of the Bible that we have, the St. Augustine's Bible, ultimately can be turned into also a very large digit. In fact, every book that's on our bookshelves here, every book that's on that Dr. Briel owns, which is quite honestly a lot of books, everything that has been written, every piece of music that you listen to on your way to and from work or dropping your kids off here or whatnot, those are digitized pieces of music, which means the sounds are given numbers. So the songs that you listen to, whether it's vocal or orchestral or what have you, is a digit. And those songs are found in this list of numbers, not just once or twice or 3 times, but infinitely many times. Every song that will be written in the future, before it's even performed, is already in there. Because it can be digitized, and that number already exists. Every book that will possibly be written in the future, maybe, maybe not, is already in that list of numbers, the natural numbers, 1, 2, 3, 4, 5, infinitely many times. The version of Hamlet, where Fortinbras says at the very end, "Go, bid the soldiers stomp," as opposed to shoot, is in here infinitely many times. Every piece of created reality, if it can be explained in any sort of words or otherwise, is in this list of infinite numbers, not just once or twice, but infinitely many times. Now, that's an infinite list of books, or infinite list of numbers. So to have infinitely many things, infinitely many times, okay. I can buy that a little bit. Let's then bring it down here a little bit. What if I change this here? This is book, right? But without the zeros. That's book right there. Okay. I'm gonna do some pretty heavy work mathematically here, so hang with me. Ready? There we go. I made it a decimal. Now the word book is a decimal that's pretty close to 1, but not quite. Right? So if you think about the number line, I'm trying to bring all these difficult areas up here. But this number, the word book, is probably right about there. Agreed? Okay. Now, if I added zeros onto the end of this, it doesn't change the number at all. That did. I've divided by 10 in this case. So now I'm close to, over here, close to 0.1. Now I'm even closer to 0. And you can see what's going to happen is that all these things that were digitized into natural numbers now infinitely live between the number 0 and 1. All of Shakespeare plays, all of the translations of the Bible, all of Dante's stuff that we have here, everything that could ever be explained in the world, appreciated, and all the stuff that never made it, it's already there. Every story that your family holds that everybody has a different story about, right? All those things you argue about what actually happened, what didn't, they're all in there. They live between 0 and 1, infinitely many times. That's pretty stunning. Because if I wanted to, I could do this and go about the whole same thing. And now they live between 1 and 2 infinitely many times. Change this 1 to a 2. And now they're between 2 and 3 infinitely many times. That's extraordinary to think that all of that kind of just concentrates into that small area between two numbers, 0 and 1. All the decimals in there. Now, there are plenty of decimals that live between 0 and 1 that are absolutely meaningless too. You try to translate them with this, it would just mean nothing, absolutely nothing. So there's all sorts of garbage in there, but there's also all of created reality. All that has been, that currently is, and that will be, is already just waiting there for us. That's remarkable. Okay, I'm not done. So I'm going to create what I've termed the super number. We're going to call it S. And super number is going to look like this. Have you gotten the pattern yet? Okay. So it is just the natural numbers that I'm just putting after a decimal, no commas between them or anything else. This is a single point on the number line. It lives somewhere between 1/8 and 1/9. Okay? 1/8 is 1.125, 1/9 is 0.1 repeating. So it's kind of in that ballpark. But if I'm writing out the super number, eventually I'm going to come across the word book. Not just once, not just twice, but I'm going to come across it infinitely many times. And eventually I would come across Shakespeare's Hamlet. Not just once, not just twice, etc. All of the books we have here, all the songs, all the created reality, in a single point, not just an interval between 0 and 1, but in a single point, something that doesn't even have any dimension to it, is able to contain all of created reality and then some. There. Now, to appreciate the kind of mathematics that goes behind all of this, to understand it and to think about it and just be awed by it and want to know more and want to tell their parents when they get home about it, That kind of love for mathematics is what we're trying to do here. That's what distinguishes us. We want them to fall in love with the topic, and if they don't fall in love with it, they would at least understand why somebody would, because it really has something significant to it. And they're willing to work through these hard times of pre-calculus where we're trying to divide these numbers or these polynomials into other polynomials and break things apart and understand the graphs of it. And it's just laborious at times. But a year ago, I went to a woodcraft, a wood turner's, he held a seminar, and I went down and took 3 days of classes with him. And he said, you only can get creative when you have skill. Once you have a skill set in place, then you can really be creative. And more than anything, that's what I want my students to be, is to be able to be creative with the mathematics, to break free of all the tedium that has bogged them down in their grade school years of long division and multiplication tables and all these things that are just such a drudgery and whatnot. But to be free and ask questions and to love it and to understand it and just, well, marvel at it and let it take us in like a piece of beautiful music would at the end of a day that we're just trying to relax. If mathematics had its proper place in society, that's the way it would be. Something that we could just savor because it's beautiful. So, if anything sets us apart is for mathematics, that's it right there. I want them to be able to savor it, to appreciate it. If they never use it, I'm fine. Math is not there to be used. It's there to be savored. So, that's my shtick. I'd love to open it up for any kind of conversation, any kind of questions you have about mathematics in general, our approach to it, any situations you might have that we could discuss, anything.
Why don't we start with some Q&A, if anybody has just a question off the top of their heads in response to this or otherwise, and then see organically where that leads us conversation-wise.
Yes.
Because how do you build skill, like by repetition, or how do you build skill in math? Because some of the angst or like math avoidance comes from the hard work of building skill. So just I'm just gonna riff on building skill before.
So yeah, part of it is how you actually build the skills. So it can be, we can spend a lot of time on, I'll just go with long division because I still have such a bad taste in my mouth. But,
I'm giving my kids as a homeschool mom a bad taste in their mouth about long division. So
yes.
please.
So our approach is that we spend some time on it,
Yeah.
but then we move on.
Okay.
And the idea is that there's a spiral and eventually we come back to it,
Sure.
but their minds are a little bit more mature, they can understand a few more things, but we move on and we come back to it, as opposed to just stay and stay and stay, and that's all we do for, weeks upon weeks upon weeks, is that we move on and we look at other things. And then there are times when we can come back to it a little bit higher, a little bit deeper, and hopefully their minds have actually progressed some, so they could look back on it and say, it makes sense now.
Mm-hmm.
I remember in college, I took calculus in high school, I took calculus 3 years in college, and it wasn't until my senior year where I took this really abstract course called real number analysis, where we looked at the idea of derivatives, kind of the basics of entry-level calculus, and all of a sudden, it wasn't until senior year of college, it's like, oh, that's it. I wish I had known that way back in high school. Back then, it was just formulas and just plug and chug, and just you get an answer. If it's right, it's right. If it's not, go do it again until you get it right. And now I saw it. Now it just made sense. Everything just kind of fit together. So it's coming back around and seeing those things a second time, a little more complexity, a little more maturity, that all of a sudden there are these moments of illumination that help them to see what it is. So otherwise the drill will just grind them into math haters.
You talked about 8th grade algebra being kind of a pivotal. Can you talk about the progression, 8th to 9th, and what you expect to see thematically? how it builds.
Sure. So our 8th grade is all algebra and X's and Y's and squares and quadratic formula and all the rest. And what I try to do also is I will show them every now and then a piece of calculus that they can partially at least see and understand. So when we study lines and the idea that there's a slope of a line, in calculus, what we're interested in is we graph a curve like this, and you say, well, what's its slope? Well, how do you talk about a slope of something that's curvy like that? A straight line has slope. Then we introduce this idea that there's this thing called a tangent line for every point on it, on a curve. And we're able to figure out a way to find the slope of a tangent line. And I walk them through some of the basics and said, well, most of the stuff you need some fairly sophisticated math to do, but at least you get a feel for what we're doing. So an 8th grade question about slope actually gets translated into this idea of calculus as well. So you give them a little bit of a feel that there's something really worthwhile coming down the road. And that understanding slope at the 8th grade level is really helpful if we're going to understand slope at 11th grade level. So we go into geometry as well, and we talk about all sorts of things, similar triangles, areas, volumes, and all the rest. Because the other big question of calculus is actually quite simple. We know the area of rectangles, we know the area of triangles and circles and polygons. You know, there's ways we can find areas, all these different shapes. But what about something that's irregular on a graph? This is just, for decades, this is the same function I've always used, just like this. I don't know why I do that. So what if you walled it off here and here, and asked the question, well, what's the area of that region? It's a simple question in that it's all closed off, so it has a specific area. How do you find it though? Because it doesn't fit any of the equations that we've developed in geometry. And we've had full class discussions about this in geometry, about how we could possibly do that. I just let them go. It's like, give me some ideas. What do you think? What will happen? They come really close to what Isaac Newton did when he first proposed the idea of how to solve the problem of area. Really close. It's amazing. So the idea of progression here is that we're both building up some skill sets, say of geometry, of algebra, of functions. I'm showing the 9th graders right now how to use their graphing calculators to go and find certain things that they couldn't find otherwise. So that's a skill set in and of itself. They get to 10th grade year, they get to more sophisticated ideas like trigonometry and matrices and conic sections and all these little areas that just need to be all in place so that when we get to calculus, we can reach into the bin and pull it out and say, I remember what this is, or maybe with a little bit of review. Okay, that's the equation of an ellipse, or that kind of thing. So slowly we're just kind of building stuff up. I don't expect them to remember everything I teach them at all. I don't remember all the mathematics myself. I have to look stuff up. So it's not a sin for them to go back and look it up and go to the back of a textbook and find something and say, what was that again? I know we've talked about it before, I don't remember. Even today in 9th grade, we're doing these things about complex numbers, so just a really complicated system of numbers. And we talked about it back in January. I looked at them and said, you remember? And then that's when the crickets cued. And I said, nope. So I said, okay, 15-minute complex number review. Here we go, you ready? We did it on the board, and 15 minutes later, they all were shaking their heads like, okay, I got it, now let's go. Let's haul on this. So it's always coming back to it. There's no way that they're gonna remember everything we teach them. It's just, the volume is just too great. But if we can remind them of it, get them to think about things well, then that's when you get the head shakes. Like, okay, I'm good, let's go now. To require them to remember everything is just, I think that's where we are distinguished from other schools as well, where exams and whatnot are just memory based. You have to memorize all these different things. I'd rather give them a cheat sheet, so to speak, with equations and theorems on it, and then give them problems to work on. You got to use these, but you got to then solve the problems. That's the critical thing. Can you actually go and solve things? Can you apply it? Yeah.
Any tips for kids who understand concepts really well, but then just go really fast and make a lot of errors? So they're just like, a lot of them, like, yeah, I got this. Boom.
Asking for a friend.
Yeah.
The math comes back and eventually bites you pretty good. So I was that way.
Okay.
You couldn't just get out of my way. Show me how to do it, get out of my way.
Yeah, exactly. Yeah.
I'm not gonna slow down. And then turns out you gotta slow down because it gets really hard really fast.
Yeah.
It's just a lesson that they learn. Yeah.
Okay.
Yeah. I don't ever really worry about that.
Okay.
I do try to insist that they show their work, only because when they make a mistake, this happened in one of my classes today, he couldn't even read his stuff. He's like, I didn't get the right answer. It's like, well, what happened? It's like, I don't know, I can't even read this. Well, we talked about this, right? Yes. In that sense, teaching girls is really wonderful because they're so meticulous in their work. Oh, about a boy?
Yeah.
Oh. Wow, yes.
I have a question. When a child comes in ninth grade and they don't have a good algebra basis, what do you do?
So, actually, my ninth grade class, almost everybody in the class was like this year. It took me a while to kind of figure them out and see where they're at. So this year we quit geometry about 3 or 4 weeks early and just did a intensive algebra review. And anybody that's going to transfer into ninth grade, that's probably where they're coming from, is they just don't have a very good algebraic background. So we review it, we go through it, we explain it. The difference between an 8th grade mind and a ninth grade mind is substantial. And so trying to understand the abstractions of algebra in 8th grade work well for some and just don't work well for others. But if you can get them back a year later, they can see the nuances a little bit better. So in our ninth grade program, we just have that kind of written in, is that we're gonna work the algebra. We need to do that more and more. So, and like I said, you get them in ninth grade years, like they just see things. They see things so much clearer than in 8th grade. So.
So at my kids' current school, they have, I think maybe starting in 5th grade, they kind of have different tracks.
Mhm.
You know, kids who maybe go slower, go quicker. So I have a kid that's in the slower class, I have a kid that's in the advanced class. How would you, or is there a way to accommodate for that here because it sounds like everybody's in the same math class per grade.
They are.
So do you do any type of individualization for maybe, like my son is often like, he hates his homework because he's got it and he's got to do 15 problems, and after 4 he's like,
What's the
this is
point?
boring. You know.
Let's see. Just because of my experience, I can accommodate a student that's really advanced and just give them some work to do while I go and work with some of the others that need more help. And that typically works just fine. I do have a 7th grade boy that's in the 8th grade math class right now, and we don't really like to do that a whole lot because it really messes the schedule up tremendously. But
Yeah.
in this case, it was necessary because he already had all of the 7th grade mathematics in place. And he's seeing new things right now, and it's just really delightful for him to do that. Most of the time what we do is we just work within the classroom.
Yeah.
And advanced students, I can give things for them to do that are appropriate for them, and then I can spend more time with those that just need more help. And given the small classrooms that we have, that's actually really easy to do.
Yeah.
But we want them all together
Yeah.
as much as we can.
If I could actually just add on to that, this is actually where another part of our education model is very critical, not just for mathematics, but for other disciplines as well. Small class sizes are absolutely necessary for the kind of individual coaching that we put at the middle of our pedagogy. So it's not just with math, but also with composition and literature and language. The ability to have a group of students that allows for the teacher to give individual attention to each child is extremely necessary to be able to coach them in skills across the board without them hitting a point of exhaustion because they've been given the same set of 20 problems that's designed sort of for the average but not actually existing child that's in the class, if that makes sense.
And then the teachers are always ready to meet with any individual that needs extra help on a regular basis. I've found over the years that 5 or 10 minutes, a couple times a week, is more important than all of the classroom time we have. Just that individual time where I can understand the student and they can ask their questions and not feel repressed or embarrassed or anything else. We can get them over a hump that day, and then the rest of the week they can go on. So, and I enjoy just sitting down with a student and just working it out and helping them see it.
So it seems to me like math is different today from how it was when I was in school. That was to say, the way that
It's taught
multiplication is
different.
done. It's taught
Yes.
differently. The methods, the processes can be different.
Yep.
And as you know, like the multiplication, the way that we tend to write it down is different from, say, Russian peasant multiplication, which you may have heard of, which is involves summing digits and dividing by 11. So you should look it up. It's kind of fascinating. But it seems like there's like a history to the way that we do things now, right? And you mentioned the way that Newton developed the calculus, and Leibniz did too, right? And do you ever incorporate the history into teaching
yes.
of math too?
Yes, I love the history. It's such a human endeavor to watch these things happen.
And the students respond to that.
Yeah, I think they do. Positively, I think their view of mathematics is that it just kind of fell out of heaven from God, and that it's here essentially to torture us for a long period of time, except for those that really like it. But to understand that calculus itself, Newton and Leibniz, they presented everything, but it was probably 200 years before everything was really formulated and settled with calculus.
Right.
It took that many mathematicians that long a time to get the definitions and the proofs and the theorems right, so that it didn't have any holes in it, logical holes in it. So those are really important for them to understand, I think.
So it sounds like you have a firm opinion on whether math was invented or discovered.
I do. Are you asking to hear it? So, when we exit here and get some refreshments out there, where the food is at is on these platters that I made out of wood. I have a wood lathe in a shop in my house. I would say two things about that. I made the bowls, but I did not make the wood. And when I got the wood, which I would say God himself made in all of his providence, I don't know how he did it. I don't know how it got here, but it was my choice to shape it that way. And so with mathematics, I think you look at, say, the natural numbers, it's pretty easy to see why they're natural numbers. What we call them that is because they seem to belong to nature. Quantities are just out there, whether it's sand on a seashore, or it's blades of grass, or it's number of trees in a forest. How people trade with numbers we start there, right? So that seems to be natural to this world, is quantities, and we've put some symbols to those quantities. After that, we've done a lot with those things, right? We came up with the idea of zero. We came up with the idea of negative numbers. We came up with the idea of fractions and decimals and really strange numbers that are out there. Super number, for crying out loud. It's a very strange number. You can't write it as a fraction. You can't write it in any other way than this way itself. But it's got some really interesting properties to it. We did that. But what we're doing is we're taking the things that are already natural and forming them. Kind of like I took something that was there in the wood and was able to form it into something. So, as a lover of J.R. Tolkien, he looks at us as humans as what he calls sub-creators. So we are made in the image and likeness of a creator, and so there's this idea of creating that is deeply instilled within us, to make something out of something that's already there. Mathematics is doing just that kind of thing. It's taking something that's already there and building off of it. And there are properties of numbers that you cannot violate. If you start to violate them, nobody's going to buy it. It doesn't work. So you have to stay within certain bounds, just like I have to do with the wood. There's just certain things you cannot do with it. If you turn it too thin, it's going to break, it's going to fall apart. If you turn it too thick, it doesn't look as good, etc. If you don't sand it, if you don't finish it, it's going to discolor and all the rest. You have to do certain things with it. Numbers have the same kind of thing. It's that here's some things you can play with, here's some things you can build with, go with it. I had a class in college where we started with the numbers 0 and 1, and we built all the way to calculus, just with some basic definitions all the way through. It was phenomenal and so hard. But that's what you can do. You can take some basic building blocks and go all the way to something that's really exquisite and extraordinary. So it's a little of both. Mathematics was something that we found already existent in the world, and then we took it and we started creating with it. This is what we have. I also think that when God made the world, he made it mathematically. In that, for some reason in his great wisdom, he left his fingerprints on creation. And to understand creation properly, mathematics is one of the clearest and most accessible way to understand so much of his creation. So, why did he do that? We don't know, but he did. And when we study mathematics, we're actually getting into kind of his mindset as how he did these things. That in itself is really worthwhile to do. So.